After spending an entire week orbiting the Earth, the space shuttle must now face the absolute most dangerous and terrifying portion of its entire mission. A brutal, fiery plunge through the Earth's upper atmosphere, screaming at speeds so extreme they literally tear air molecules apart, wrapping the spacecraft in a blinding cage of superheated plasma. This lethal re-entry is where the space shuttle truly proved it was a legendary, one-of-a-kind spacecraft. It was a radical, almost impossible concept, a vehicle designed not only to survive the hellish temperatures of re-entry, but to transition into aerodynamic flight. This required engineers to meticulously sculpt its wings and tail, balancing the needs of an unpowered glider with the extreme demands of a re-entry vehicle. This is the insane, mind-blowing engineering behind surviving re-entry. The high-stakes procedure begins upside down and backward, with a critical 2 to 4 minute burn of the orbital maneuvering engines. Traveling at a blistering orbital speed of 7 kilometers per second, the OMS pods must reduce the shuttle speed by just 0.1 kilometers per second, a mere 1.3% of its velocity, to drop its orbit enough to collide with the Earth's upper atmosphere. It is a terrifyingly precise maneuver. Slow down too little, and the shuttle will overshoot its razor-thin window of success, skimming off the upper atmosphere and bouncing helplessly back into the void of space. After all, the orbiter has wings designed to generate lift. But slow down too much, and the orbiter will plunge through the atmosphere too quickly, hitting the thick lower air before shedding its speed, resulting in catastrophic, fatal overheating. This incredibly narrow path between survival and destruction is known as the entry flight corridor. Once this delicate retrofiring sequence is complete, the next terrifying phase of re-entry begins. The reaction control thrusters flip the shuttle around, pitching it up 40 degrees to slam into the atmosphere at a staggering 30 times the speed of sound. At this speed, air molecules are violently ripped apart, creating a glowing, superheated cloud of charged plasma around the lower surface of the orbiter, with peak temperatures skyrocketing to a blistering 1650 degrees Celsius. Absolutely nothing like this had ever been attempted in human history. A blunt body capsule designed purely for thermal protection is already a massive engineering challenge. But adding the aerodynamic needs of a winged aircraft makes the task almost impossibly difficult. Fortunately, NASA had a crucial test run in 1959 with the X-15, the fastest plane in human history. It dramatically advanced our understanding of hypersonic flight, providing invaluable lessons that were built directly into the space shuttle's design. However, the X-15 had one massive advantage over the space shuttle. It did not need to launch itself into orbit. It did not even launch from the ground, instead dropping from the belly of a B-52 bomber. This allowed the X-15 to use a state-of-the-art, heat-resistant aerospace metal called Inconel X, with a maximum operating temperature of 980 degrees Celsius. But the space shuttle could not use this heavy metal. Inconel X is simply too heavy, nearly 80% heavier than an equivalent aluminum airframe, a fatal flaw for an aircraft designed to be carried all the way into orbit. Believe it or not, the space shuttle's frame wasn't built from ultra-tough Inconel X. Instead, engineers used lightweight aluminum, a metal that melts under extreme stress, with a pathetic limit of just 177 degrees. That is 5 times weaker than Inconel. Yet, during re-entry, the orbiter had to survive temperatures 10 times hotter than that limit, screaming through the atmosphere for agonizingly long periods. To make matters far worse, one of the most shocking lessons from the X-15 program was that the bright pink ablative coating sprayed on for top-speed runs was a total disaster for the space shuttle. This sacrificial shield is supposed to slowly burn away, carrying the extreme heat with it. However, the X-15's coating had a terrifying habit of peeling off the nose and sticking directly to the cockpit windows, blinding the pilots instantly. This was a massive, life-threatening crisis. In a moment of sheer desperation, engineers actually considered strapping live explosives to the cockpit glass, planning to blow the outer window pane completely off mid-flight just to clear the pilot's view for landing. Fortunately, they chose a less insane route, installing a mechanical eyelid over the left window that stayed shut until the high-speed run ended, leaving one clean window. But this crude fix triggered a new aerodynamic nightmare. The open eyelid acted like a mini wing, causing the plane to violently pitch, roll, and yaw out of control. Even more terrifying, this coating turned into a literal bomb when mixed with liquid oxygen, capable of detonating from the slightest bump. This was a lethal hazard for any aircraft using liquid oxygen, but for a massive space shuttle packed with 500,000 liters of the volatile oxidizer, it was a ticking time bomb. To top it all off, the coating was strictly single-use, which would drive refurbishment costs through the roof. The space shuttle demanded a revolution in engineering. As the orbiter plunged back through the atmosphere, its nose and wings slammed into the air, bearing the brunt of the punishing re-entry heat. High-pressure shockwaves wrapped the vehicle in a shroud of superheated plasma. If this inferno breached the delicate aluminum framework inside, it would mean instant, catastrophic destruction. This nightmare became a tragic reality for the Columbia shuttle when its wing's leading edge was damaged. To save the orbiter, engineers had to keep this superheated plasma as far from the skin as possible. Every curve of the nose, wings, and belly was meticulously shaped to push the deadly shockwaves away from the vehicle. Schlieren imaging reveals this hidden danger perfectly. Watch how a sleek, missile-like vehicle slices through the air with lethal efficiency. As it does, it generates a powerful shockwave attached directly to its nose, angled by its extreme Mach speed. This shockwave is a zone of crushing high pressure, and with that intense pressure comes blistering, destructive heat. The consequences are catastrophic, as DARPA discovered the hard way during tests of their sharp-nosed hypersonic vehicle, the HTV-2. Within just 9 minutes of hitting the atmosphere, the blistering 1900-degree heat breached their metallic skins, causing both experimental craft to violently disintegrate. While the HTV-2 merely gathered raw hypersonic data, the legendary space shuttle faced a far deadlier challenge, surviving this extreme, melting inferno over and over again with barely a scratch. Engineers weaponized physics, using a radical blunt-nosed design to deflect the heat. This created a massive protective bow shockwave, trapping a vital layer of cooler air to shield the spacecraft's vulnerable skin. Every single curve of the shuttle's belly was meticulously sculpted to exploit this mind-bending phenomenon. Its bulbous nose seamlessly morphs into a massive, blunt triangle. This genius geometry deflected the lethal heat away from the fragile sidewalls, which relied on much weaker insulation. 7 agonizing minutes into re-entry, the orbiter has plunged 50 kilometers down. Yet it has barely shed a fraction of its blistering speed. Now, it collides with the absolute peak of re-entry heat, a violent clash of extreme speed and thickening air. A terrifying shroud of superheated plasma engulfs the craft, completely severing all communication with the outside world. Free electrons within the raging plasma create an impenetrable shield, choking out all electromagnetic signals. A deafening, tense silence that will drag on for 12 agonizing minutes. Flying completely blind, the shuttle must rely entirely on its internal systems to maintain a precise 40-degree angle of attack. Controlling this critical angle while screaming through the sky at over 6 kilometers per second is a monumental feat. It demanded an absolute beast of a control surface. The standard wing elevons were completely useless here. Enter the unsung hero, the massive rear body flap. Positioned directly beneath the main engines, this giant slab of metal was wrapped in ultra-high temperature armor. This crucial flap doubled as a desperate shield for the shuttle's main engines. Without freezing liquid hydrogen pumping through the nozzles, the engines would melt instantly without this protective barrier. During the shuttle's 3rd historic flight, the Kuiper Airborne Observatory soared directly beneath the falling spacecraft. It captured a stunning top-secret infrared image of the shuttle's glowing underbelly to prove NASA's wildest mathematical theories. And the results were shocking. The nose and wings were glowing at a blistering 1,500 degrees Celsius, a temperature that would instantly liquefy the aluminum frame underneath. To survive this hellfire, the leading edges required the most advanced material ever conceived, reinforced carbon-carbon. This revolutionary composite was born from the cutting-edge era between the X-15 and the Space Shuttle. But creating this supermaterial required a secret multi-step process. It started out normally enough, shaped from a standard carbon fiber weave and glued together with a basic resin. But the savage heat of re-entry would instantly ignite that resin, destroying the ship without a crucial transformation. That is where the extreme post-processing came in. Locked inside a vacuum chamber, the material was baked until the resin decomposed, venting away hydrogen and leaving behind pure, indestructible layers of graphite. This created a dense maze of pure carbon, capable of defying temperatures up to 1,500 degrees Celsius. A legendary shield, standing defiant against the absolute fury of hypersonic flight. Guarding the orbiter's wings are 22 extreme carbon panels, sealed tight to cover deadly expansion gaps, a critical fix born from a terrifying, near-fatal lesson learned during the wild days of the X-15. To unlock the secrets of brutal hypersonic heat, engineers coated the experimental X-15 in a highly sensitive, color-changing thermal paint. But after one blistering flight, it returned scarred with bizarre wedge-shaped burn marks bleeding from the wing joints, tiny gaps designed to let the Inconel metal skin flex under extreme stress. Violent, turbulent airflow was creating localized superovens, rapidly pumping lethal heat directly into the aircraft's metallic skeleton. To stop this disaster, engineers shielded these gaps with floating strips of ultra-tough Inconel. Today, these advanced carbon-carbon panels perform that exact same life-saving job. But a far more dangerous threat remained. Carbon actually conducts heat, a recipe for catastrophe when building a thermal shield. Hurtling through the atmosphere for 15 agonizing minutes at a blinding 6 kilometers per second, the shuttle remains completely cut off, trapped inside a blazing shroud of superheated plasma. Under this relentless thermal assault, the conductive carbon could easily leak this deadly heat straight into the fragile aluminum frame. Direct contact would be fatal, instantly melting the metal structure and triggering a catastrophic structural failure. To prevent total destruction, the panels were isolated using heavy-duty Inconel brackets and bolted down with matching Inconel fasteners. This superalloy acts as a thermal dam, absorbing the intense heat from the carbon without letting it bleed into the vulnerable aluminum below. Yet, even this wasn't enough to save the crew inside. A secondary defense line of high-tech insulating tiles had to be packed beneath the carbon shields, matching the armor protecting the entire belly. The ill-fated Columbia carried 32,000 of these tiles, divided into two critical types, low-temp white and high-temp black. Shockingly, both relied on ultra-thin silica fibers, which accounted for a mere 10% of the tile's actual volume. The other 90% was pure trapped air, creating an incredibly lightweight, heat-defying barrier capable of surviving extreme temperatures. The real secret lies in their specialized outer coatings. The belly tiles were armored with a dark high-tech borosilicate and tetraboron silicate glass glaze. This dark shield aggressively radiates heat away before it can penetrate the spacecraft's vital organs. It's black for the exact same reason the legendary SR-71 Blackbird is black, Kirchhoff's law of radiation. This law dictates that a perfect heat absorber is also a highly efficient heat emitter. Since hypersonic friction generates far more heat than the sun ever could, radiating that energy back into space is the ultimate priority. So why wasn't the entire space shuttle painted pitch black? Because the shuttle faced a completely different, far more hostile environment. It actually left the planet. And in the vacuum of space, the sun's raw, unfiltered radiation becomes absolutely punishing. With missions lasting up to 17 grueling days, this lethal heat threatened to cook the crew alive inside. Massive radiator panels worked overtime to dump the heat, but to keep them compact, they had to reflect every bit of radiation back into the void. That's why they were painted a blinding, brilliant white. These high-tech tiles featured a specialized glass armor infused with aluminum oxide to achieve that signature stark white shield. This crucial layer also waterproofed and reinforced the otherwise fragile, porous material. It was the ultimate high-stakes jigsaw puzzle. 32,000 individual pieces engineered to absolute perfection. Every single tile carried a unique serial number dictating its exact position, custom shape, and critical thickness. The process began by blending fluffy cotton-like silica fibers with pure water. This slurry was cast into massive blocks and baked dry in a giant microwave oven. Once cured, they were sliced into workable sheets. Varying from 25 to a thick 127 millimeters, the thickest tiles could withstand a mind-blowing 1280 degrees Celsius. Advanced computer-controlled milling machines then carved these sheets into ultra-precise shapes, matching their specific serial numbers. As the spacecraft finally emerges from the terrifying communication blackout, the intense re-entry heat penetrates deep, forcing the aluminum airframe to expand. This spells disaster because these heat shield tiles are completely rigid and shockingly fragile. The flexing metal could easily shatter the tiles, opening a deadly path for superheated plasma to rip through the ship. Engineers desperately needed a way to let the structure flex underneath without popping the tiles off into space. Their genius solution? Bonding the tiles to a shock-absorbing layer of flexible Nomex felt. This Nomex fabric allowed the metal structure underneath to stretch and flex, absorbing all that destructive tension before it could ever reach the fragile tiles. This vital thermal shield was bonded to the spacecraft using a surprisingly common consumer product, a bright red ultra-high temperature silicone RTV adhesive. To stop the tiles from smashing into each other, microscopic gaps of less than 2 millimeters were meticulously left between them. Fortunately, the dangerous turbulence triggered by these expansion gaps only threatened the wing's leading edges, meaning the rest of the shuttle could leave these gaps exposed. In areas facing less extreme heat, they deployed flexible thermal blankets. Woven from high-temperature silica and Nomex fibers, these materials were stitched together using the very same fibers, giving the spacecraft a unique quilted blanket armor. The Nomex fabric could survive up to 370 degrees, while the silica fabric endured a blistering 650 degrees. Far lighter and simpler to replace than the rigid tiles, these blankets were glued straight to the hull with that same bright red silicone RTV adhesive. Emerging from the blackout, the craft screams through the sky at a blistering Mach 12, 4 kilometers per second, cruising 45 kilometers high, 4 times higher than a commercial jet. Throughout this entire terrifying descent, the orbiter has held a steep 40-degree angle of attack. But maintaining such an extreme angle triggers a nightmare of control issues. The crew must somehow guide this massive craft to a pinpoint landing on a narrow runway. Steering with the nose pitched high is incredibly dangerous, especially for an unpowered glider that cannot regain energy once it is bled away by atmospheric drag. To plunge through the atmosphere and bleed off altitude, the space shuttle faced a deadly trap. It couldn't simply nose down. Engineers needed a radical trick to steer this falling brick to its runway. Their solution? A jaw-dropping, high-stakes bank. By tilting the spacecraft, they diverted its massive upward lift sideways, sacrificing altitude to steer through the sky. Witness the extreme path of a shuttle falling back to Earth. Watch the angle of attack lock in until Mach 12 before slowly dropping in the dense air. But look at this insane bank angle. As the spacecraft hurtles down, it violently rolls from side to side. The crew, already tilted 40 degrees up, are suddenly thrown sideways at a staggering 70 degrees. It is without a doubt the fastest, most extreme drift in human history. At hypersonic speeds, physics goes absolutely haywire. Crucially, the flight controls actually operate completely in reverse. Push the right wing flap down, and you would expect the wing to rise, rolling the shuttle to the left. But it does the exact opposite. Slamming that flap down into the brutally compressed hypersonic airflow triggers a sudden surge of drag on the outer wing. This violently yanks the shuttle's nose right toward the drag. As the nose swings, it completely blocks the airflow to that very wing, destroying its lift and forcing the shuttle to roll hard into the turn. So a control input that should lift the wing actually crushes its lift, flipping standard aerodynamics completely on its head in a bizarre chain reaction. Naturally, this extreme banking throws the shuttle way off course, forcing the crew to violently roll the other way to compensate. Decelerating to Mach 3, the crew deploys critical air sensors to survive the final approach. Two vital probes swing out from under the scorching heat shield, feeding speed, angle, and temperature data straight to the flight computer. Now, the shuttle flies like an airplane, but it has no engine. It is a giant glider, and the crew has only one shot to manage their energy and land. But this was no ordinary glider. Surviving the fiery hell of re-entry while maintaining flight efficiency was a nightmare engineering puzzle, made far worse by strict Air Force funding that forced the design to look more like a heavy jet than a spacecraft. Early designs took cues from the legendary X-15, featuring tiny wings that were just enough to guide a smaller shuttle back to Earth. But the military demanded a massive cargo bay, and they had one secret requirement that changed everything. They demanded the shuttle launch from Cape Canaveral, execute a covert mission, and land right back at the Cape after just one orbit. It was a high-stakes military operation designed to dodge Soviet eyes, lightning fast and completely invisible. But this created a massive problem. In the 90 minutes it took to orbit, the Earth spun 2,000 kilometers beneath the spacecraft. To make it back to the launch site, the shuttle had to glide sideways by a staggering 2,000 kilometers. This extreme capability is known as cross-range. Imagine a spaceship that could barely steer. The early X-15 design was a total dead end, managing a measly 370 kilometers of cross-range. But in 1970, North American Rockwell proposed a radical, massive delta wing concept that shattered limits, promising a mind-blowing 2,800 kilometers of maneuverability. While the dream of a fully reusable ship with crude boosters faded, those giant delta wings survived. They were engineering masterpieces, generating massive lift from hypersonic speeds down to a crawl, allowing the shuttle to glide all the way back to its launch pad after just one orbit. This was the ultimate key to surviving the hostile return from space. Yet this flying brick was notoriously hard to control. With zero engine power during landing, pilots had exactly one shot at survival. One mistake meant disaster. There was absolutely no room for error, which demanded brutal extreme training. In 1973, NASA modified 4 Gulfstream jets into terrifying simulators. To mimic the shuttle's insane aerodynamic drag, these jets flew with landing gear down, engines screaming in reverse, and flaps flipped upward to kill all lift. Flying this way meant energy management was a matter of life and death. Drop too low too early and you crash. Guided by ground control, pilots aimed for a tight 5,800-meter circular path right next to the runway. They had to hit this target perfectly. The instant they hit this circle, the shuttle plunges into a terrifying spiral. Hurling forward at Mach 0.8, the wings endure extreme, bone-crushing pressure, more intense than any other moment of the entire re-entry. Falling like a stone, the shuttle drops to 3,000 meters, slowing to Mach 0.5. Suddenly, it noses down into a steep 20-degree dive, way steeper than any commercial airliner, using a split rudder to bleed off excess speed. This wasn't just a normal rudder. It split wide open, deflecting 62 degrees to act as a massive brake. At the absolute last second, the landing gear drops, and the pilot pulls the nose up to cushion the impact. The wheels hit the tarmac, and the speed brakes burst open. But at 360 kilometers per hour, stopping this beast is a nightmare. That is why Cape Canaveral's runway is a massive 4.6 kilometers long. As the nose slams down, the pilot stomps the brakes. Inside the wheels, carbon-lined beryllium discs crush together to fight the speed. And on mission STS-49, they unleashed a secret weapon, a massive drag chute deployed from the tail. STS-49 marked the jaw-dropping debut of Endeavour and its wild, explosively deployed drag chute. You can actually see the parachute door and sabot violently blasted from the tail during touchdown. This extreme system was designed for emergency landings on dangerously short runways across the Atlantic. For every single launch, NASA deployed elite teams to far-flung abort sites like RAF Fairford in England, bracing for a worst-case scenario. An army of specialists stood ready for the harrowing final moments of these missions. Incredibly, this massive emergency force was never once needed in the shuttle's entire history. Ground crews even rolled out colossal fans on the tarmac to blow lethal toxic hydrazine fumes away from the returning astronauts. With the mission over, the crew steps out and the shuttle is prepped for a spectacular piggyback ride home to Florida atop a modified jumbo jet, ready for its next daring voyage. It is absolutely mind-blowing that these legendary spacecraft were drafted entirely by hand, a labor-intensive art form. Today, digital engineering has completely revolutionized how we build the future, transforming these classic blueprints into reality.